Hello class and welcome to Riley's Physics Lessons. Today we're going to be going over Einstein's theory of special relativity in my simplified version. So let's start with an analogy. When we observe a rocket ship moving away from us through space, we make some assumptions like the person aboard the ship is the same mass they were when they left, that their time ticks at the same rate as ours, and that their dimensions, their length and their height, is the same as it ever was. Imagine we have a person aboard a rocket ship, and they're just hanging out, they're having fun. And here we are, here's Earth, and here we are. The assumptions that we make are that we on Earth and the person in the spaceship are both moving through space and time at the exact same rate in the exact same way. Einstein says that this is not true. When a rocket ship moves through space, it moves at incredible velocities. The fastest we humans have accelerated ourselves is to the speed of 5 miles per second. Now, don't get me wrong, this is a very fast speed. However, it pales in comparison to the speed of light. More on that later. As our space person here travels at 5 miles per second, they undergo Einstein's theory of special relativity. The theory is based on two postulates. Postulate number one, I'm going to name my notes for this one, is that all the laws of physics are the same in all inertial reference frames. So essentially, the laws of physics are always the same. No matter where a person is, how fast they're moving, or what point in time you may find them at. And Einstein's second postulate is that the speed of light is the same for every observer, no matter how fast they are moving. And for those of you wondering, the speed of light is, as I wrote here, 3 times 10 to the 8 meters per second. And we denote that with c. Whenever I write c in this lesson, I mean the speed of light, 3 times 10 to the 8 meters per second. So what is special relativity? Well, it's defined as Einstein's theory that explains how speed affects time and length through space. This is all based on these two postulates. Let's talk about that now. Let's talk about our space person. He's moving quite fast. What happens to the light that he emits? You see, let's say at the end of this spaceship there was a flashlight, and it was emitting a beam of light in front of him. Now you see, light is special because it's a wave. Now the thing about waves is they don't obey inertia. And what that means is that things produce a wave, right? You know, a duck swimming through a pond, or us holding a string that's tied to one end. Say, for example, we had a pole, and we had a string that was tied like a loop, and then we had it going out, and we were holding onto it here. When we flick it up, we would create a wave, and that wave would move along the string, and depending on how it's tied here, would either rebound the same on top or rebound on the bottom. It doesn't really matter. What the point is that this wave is going to move at a velocity. And that velocity depends on things like the thickness of the string, the weight of the string, maybe the string was soaked in water, the quality of the string, and the air around the string. You see, imagine I was running, and I grabbed the string while running, and I flicked it. What would happen to the velocity? Well, those who understand inertia say that when an object is moving at a velocity, and then it is, say, thrown, it moves with the speed of the throw plus the speed that it was already moving at. So say I was holding this marker, and I was running at 5 meters per second, and I threw it at 2 meters per second, it would have a speed of 7 meters per second. You see, that doesn't happen with waves. Even if I was running at light speed and I flick the string, this wave on the string would continue to move at the same velocity as if I was standing still. And that's because waves do not depend on inertia. They depend on something called a medium. Now let's talk about mediums. So what is a medium? A perfect example of a medium is air. Air is a medium, and what are the waves that travel through air? They are sound waves. You see, sound cannot exist without air. All around us, let's say you have a room, which exists here on Earth, and it has air in it, and you have a speaker right here, and it's going to produce a sound wave. You see, the sound wave starts out something like this, and it grows, and grows, and it'll rebound off the walls, and those rebounds will create more waves, and there's a huge chain reaction with waves where they cancel out or they amplify, making louder, quieter noises, etc. It doesn't really matter. What matters is sound like this cannot exist without the medium of air to travel through. You see, in space there is no sound because there is no air, and that's why there's no sound in space. But let's think about light for a second. You see, light travels through space, travels through the entire universe. But what's its medium? Well, for a long time, we humans believed that light traveled through a medium known as the ether. But that was disproven. And so now we know that light doesn't travel through a medium. Instead, it kind of creates its own. You see, light is an electromagnetic wave, which means that it creates a magnetic wave and an electric wave, which cancel each other out, essentially moving light beams, known as photons, through space. Now, the reason why light having no medium is so important is because there is no change in environment that can change the speed of light. It'll always move at the speed of light. But you see, since light has no medium, light's just moving. There's nothing going against it. We would think that our spaceship emitting light out the front, let's say the spaceship is moving at 90% the speed of light. So 0.9 times the speed of light, 0.9 c. Let's say the spaceship is moving at 0.9 c, and it emits a beam of light. What do you think the speed of light would be? Since it's a wave, it doesn't obey inertia, so it's not going to be, it wouldn't be the speed of light plus this. It doesn't obey inertia, it's a wave. You might think, oh, this is moving at 0.9. The speed of light, maybe it is moving at the speed of light, but we're moving at 90%. So what we perceive is 10% the speed of light. You would be wrong to assume this. You see, light, no matter how fast you're moving, will always appear to be moving away from you at the speed of light, c. So let's say we have this spaceman in here, Bob, and he's got some magical way to measure the speed of light. He's moving at this incredible speed, and he expects to see light leaving at only 0.1 times, so 10% the speed of light. But what he sees is the normal speed of light. How is this possible if light has no medium, and if light is a wave, then this disobeys all the laws we know? Well, Einstein says no. This perfectly obeys the law of relativity. This is how Einstein derived his second postulate, which we mentioned earlier, that the speed of light is the same for all observers. So how is this possible? What is happening so that the speed of light is conserved? Well, two things are mainly happening: time dilation and length contraction. Let's keep this, and let's say Bob was moving at 90% the speed of light. He would still see light moving away from him at the speed of light, even though this shouldn't be possible if light is a wave. So how does he see this? Well, unbeknownst to Bob, he has undergone time dilation and length contraction. So the two founding concepts of Einstein's theory of relativity are time dilation and length contraction. They are mathematical rules that show us why the speed of light is the same for all observers. Take this example I've made here on the bottom. We have a rocket traveling at 90% the speed of light next to a light beam traveling at the speed of light. Essentially, even though this person in this rocket is traveling at this speed, they will still see this beam of light moving away from them at the speed of light, not at 10%. So what that means is that this distance that they're measuring, in the time that they're measuring it, must be changing. You see, time is not the constant that we thought it was. And so what this means is that the speed of light, c, is the only constant. You see, we have a spaceman and a rocket, and we also have us observing him from planet Earth. That's us. You see, time is not constant for both of us. It is not the same, and neither is length. This constancy of speed of light forms the bedrock of Einstein's theories. According to special relativity, as an object moves closer to the speed of light, similar to this rocket, time dilation becomes more pronounced. So the faster you're moving and the closer your speed is to the speed of light, the slower your time ticks relative to, in this case, us. So there's a person on the rocket, we call him Bob, and there's us. Bob's moving at 90% the speed of light, and his time is drastically slower than ours. And this makes sense, and it exists because of the fact that the speed of light has to be maintained. Let's explore this through a hypothetical scenario involving two twins. We're going to change this person, and they're going to be Alice. And the person on the rocket ship is going to stay as Bob, and they're twins. Bob embarks on this journey aboard his spacecraft, traveling at 90% the speed of light, while Alice remains stationary on Earth. From Bob's perspective, aboard the spacecraft, time passes normally. His experiences and actions unfold as expected. However, from Alice's perspective on Earth, things appear differently. Alice sees that time for Bob is moving slower. The mathematical underpinning of this effect can be understood through the Lorentz factor, or the time dilation equation as I've written here. This value t is the value that Alice is experiencing, and this value to is the value that Bob is experiencing. You see, technically, Bob is at rest, even though he's moving, because Bob is seeing light, and Alice is perceiving light and Bob. So TO is Bob, time initial, time at rest is Bob, and T is Alice. So you see, if we were to say that 10 seconds pass for Alice, so T is 10, and the velocity of Bob is 90% the speed of light. If we did this equation, we would find that the time for Bob, TO, is 4.35 seconds. So in the time it takes for Alice to pass through 10 seconds in the universe, Bob passes through 4.35 seconds. That's what that formula gets us. So let's break down this formula. This V here represents the velocity of Bob on the spacecraft. As V, his speed, approaches C, and they become the same thing, they become 1. The number 1. They literally become the number 1. And 1 minus 1 is 0. And the root of 0 is 0. So you'll have T over 0. And if you know anything about math and fractions, is that if you have 0 on the bottom of a fraction, you get a math error. It doesn't exist. What essentially that's saying in this equation is that you reach infinity. Your time is infinite. The crux of why this occurs lies in the intertwined nature of space and time within Einstein's framework. Special relativity posits that space and time are not separate entities, but are part of a unified fabric known as space-time. As an object moves faster relative to an observer, so as Bob moves faster relative to Alex, its progression through both space and time is altered. Specifically, time slows down for the moving object relative to the stationary observer. This is why Bob moves slower. This is why in 10 seconds for Alice, 4.35 seconds pass for Bob. So from Bob's perspective, Alice is moving faster through time. And from Alice's perspective, Bob is moving slower through time. This effect is not merely theoretical, but has been experimentally confirmed on planet Earth here through precise measurements with atomic clocks on high-speed aircrafts and satellites. So you can imagine a fast-moving object, like an airplane, moving very fast for a very long period of time. If you had an atomic clock that was just sitting on Earth and an atomic clock on the airplane, after a certain amount of time, you would be able to compare the clocks, and they would be different. And that happened, and we did this, and it was true. Moreover, the implications of time dilation extend beyond thought experimentation. In practical applications, such as the Globe Positioning System, GPS, engineers must account for the slight time dilation effects caused by the orbital velocities of satellites relative to the Earth. Essentially, the satellites are so far away from Earth and Earth's gravity, they're moving through space-time, and they are experiencing time different from us. And so those satellites have to be adjusted based on that so that we get precise measurements here and there. I'll do my best to explain why it is that this must happen. Forgive me if I do a bad job. The formula for velocity has time as the denominator, right? And distance is the numerator. Velocity cannot change. The speed of light cannot change for any observer. So Alice is seeing the speed of light. She's moving, there's a certain amount of time passes by, and light travels a certain distance, and she calculates it. She says, light travels this distance in this time, so the speed of light is 3 times 10 to the 8 meters per second. But Bob's in a different situation. Bob's moving at 90% the speed of light. But what happens is that his time dilates. And so he might not notice it, but us on Earth, Alice on Earth, we notice it. We see him slowing down. And we say, we know that since his time is moving slower, but we see light moving at its normal rate, he's going to measure it, and it's still going to be 3 times 10 to the 8 meters per second, because his time is getting smaller. And when a denominator gets smaller, this value gets bigger. Imagine if we did 10 seconds for both Alice and Bob. And we did the distance and everything. What we would find if we left 10 seconds and 10 seconds is that the speed of light would be different. But that cannot happen. The speed of light cannot be different. It would be smaller. The speed of light would be smaller for Bob. We want it to be bigger. So how do we make it bigger? We make the denominator smaller. And that's what happens. Time dilates, the denominator gets smaller, the speed of light increases until it reaches 3 times 10 to the 8 meters per second. But that's just time dilation. What about length contraction? Well, it's very similar to time dilation. Length contraction, another profound concept from Einstein's theory of relativity, reveals that the lengths of objects in motion appear shortened along the direction of their motion when observed from a stationary observer, like Alice. You see, Bob's moving like this, and Alice sees him moving in this direction. What length contraction says is that in this direction, let's say this is the x-axis, in the x-axis, Bob will get shortened. So really, he'll look something like this. Now that's not to scale. This mathematical formula tells you the scale. But essentially, Bob's getting shortened like a cartoon. And this also conserves the speed of light. In the framework of special relativity, the length of an object in motion relative to Alice or an observer appears contracted by a factor known as the Loretz factor, denoted as this formula. Here, velocity represents the relative velocity between the moving object, Bob, and the observer, Alice. And c is the speed of light. As v approaches c, and as v becomes the same as c, they become 1. You have the same number over the same number, they cancel out and they become 1. Then you have 1 minus 1, which is 0. Once you have 0, you have root 0, and you have L times root 0 is 0. Everything's 0. So what we're saying with this formula is that once you reach the speed of light, your length will contract into 0, and you will not be visible. The concept can be illustrated through a simple example. Imagine this spaceship, Bob, moving at 90% speed of light, same as we always have been. If the spaceship is perceived to have a certain length, LO, when measured from within the spaceship itself, so Bob has a tape measure, he measures from one end to the other, and it's LO. The stationary observer, Alice, would measure the length of the spaceship as L. So Bob in the spaceship sees LO, but Alice on Earth sees L. And we find the exact lengths that Alice would see with this formula. We would take Bob's velocity, 0.9% speed of light. So one, subtract that value, root it, and then multiply it by the length Bob measures, but also by the length that the spaceship was when it was sitting here on Earth. And we would find the length that we would perceive. And technically, that's the true length, because the speed of light has to be conserved. And so Bob's length must contract. Let's bring it back to the velocity formula. Velocity equals distance over time. We already know what happens to time. It gets smaller. And so essentially, the length contraction accounts for the distance that light is traveling. It takes the distance and says light must travel a different distance to preserve the speed. It must travel a shorter distance. That's why the length contracts. You see, a shorter distance in a quicker time means a fast velocity. I will admit that a big distance in short time is a quicker velocity, but you see, light doesn't really care about that. Light only cares about preserving the speed. And so what happens is, although time does decrease, length also decreases. It decreases the numerator. Not so much that it has any negative effect. What this essentially does is it's a failsafe for time dilation. See, time dilation drastically changes the velocity of the speed of light. In fact, it makes it too fast. And so length shortens to preserve that speed, to make it so that the speed of light is preserved. That's why length dilation is also a key factor into Einstein's relativity. Similar to time dilation, this phenomenon arises due to special relativity, where space and time are intertwined into space-time, and the speed of light is conserved for everyone, all observers, Alice, Bob, you and I, everyone. When an object moves relative to an observer, its position in both space and time transforms in such a way that the speed of light remains unchanged from all perspectives, which we've covered. Therefore, to maintain this consistency, space and time must adjust in relation to one another, leading to length contraction and time dilation. Similar to time dilation, experimentally, length contraction has been confirmed as well in numerous ways, such as measuring the lifetimes of unstable particles, which we'll talk about in a minute. These particles, traveling close to the speed of light, reach Earth's surfaces despite their short flight times, because from their perspective, the distance to the Earth is contracted. It's shortened. The distance from them to the Earth is drastically contracted, and they can travel the distance and still exist. The muon, something like that, is an elementary particle that has such a short life, something like 1/25th of a billionth of a second, that it dies before it reaches the surface of the Earth, even though it's traveling at almost the speed of light. They are born only 25 kilometers above the surface of the Earth. So you can imagine how short their lives are, considering the fact that it takes light a fraction of a second to travel the entire circumference of the Earth, which is over 40,000 kilometers. So you can imagine how short this thing's life is. Now, let's think for a second about time dilation. We just learned that when things move closer to the speed of light, their time slows down compared to everything else. And so we would assume then, based on the theory of relativity, that even though the muon has an incredibly short life, it's almost moving at the speed of light. So does that mean that we would be able to see the muon around us? And the answer is yes. We do. We found them. They exist on the surface of the Earth because they're traveling so fast and their time slows down so much that for them, their life is a 25th billionth of a second, but for us, it's much longer. If I were traveling at the speed of the muon around you, I would be frozen in time. I mean, you wouldn't be able to see me because I'd be moving so fast, but it would look like I was frozen there, not moving, because my time is slowed down. I'm not aging. The universe would whiz by me in time. It would move so fast. And in a blink of an eye, eons would pass. But for you, it would look like I was just frozen. And the same thing goes for the muon. Even though it should die the moment it is born, it should never come even close to us. We see it all around us. Scientists, physicists find it in particle accelerators. And so it exists on the surface of the Earth. And it shouldn't, but it does. And so this proves that time dilation is a real thing. And therefore, length contraction must also be a real thing. And so Einstein was right. This ends my presentation. I hope it wasn't too confusing, and there was definitely a lot of moments where I could have explained things better. Thank you for watching.